In the previous video, we were talking about limits, the fundamental idea to calculus. Now, calculus, there's two types of calculus. We have differential and integral calculus. So we'll talk about the first one we have is differential. Okay, and differential calculus is basically concerned with this geometric problem, which is finding a tangent to a curve at a point on that curve. First of all, what do I mean by a tangent? Well, tangent comes from the Latin for to touch. So if I have some curve here, and I say I pick a point right here, the tangent is a line that just touches that curve, just at that one point. It passes through one point. Just like that. I can basically pick a point on any point of this curve, and I should be able to draw a tangent. There are some functions where I can't do this, but this isn't one of them. It's just an arbitrary curve that's I can just simply pick a point, and by eye I can just draw a tangent through it. Now Leibniz, who was one of the founders of calculus, came up with a definition of tangent, which is that it's a line that passes through two infinitely close points on the curve. So what does that mean? Well, what he's thinking in his mind is something like this. Because what we need to define a line is 2 points. Okay? Anytime I want to define a line, I just need to pick 2 points in space, and immediately I can just draw a line. But if you give me a point just in space like that, I don't know how I could draw that line. I could draw it through there or there or there. I smudge the point. We don't know. So what we need is these 2 points. So Leibniz kind of knew that. He's working with a geometric idea of what a line is. And so what he does is he lets these 2 points get really close to one another. And I'll show you what I mean. So we'll take our friends here. Oops. This is x squared. There's my... Okay. And right here is, we're going to say, is 1. And coincidentally, that value of 1, so that's 1 squared, gives us 1 as well. And what we can do is we can also pick another point, just maybe say up here. And that point here, well, let's just pick an arbitrary distance. We'll say this is delta x. And what we'll say then, this point here, it's on the x-axis, it's 1 plus delta x, which then means here, the value here is f of 1 plus delta x. And in this case, this is our function. So what he says is we can draw a line now through this. We got, boom, a line that runs right through here. Okay, so let's say that Leibniz wants to find the tangent at the point 1. So what his question would be is, what is the equation of the tangent at x equals 1. Okay. So what he does is, if we want the tangent, he starts to move this point really close. We can start to kind of walk that closer until we get really, 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 really close. We're taking it to the limit. So we're letting it approach 1. So it's getting really small. Now, why are we so concerned about doing this, taking a limit and so forth? Well, remember when we're talking about the meaningless of a function when we start to divide by 0? Well, we have to remember, what is the slope in this case? Well, the slope of the tangent, well, or just basically this line right here, if we pick this arbitrary, remember, it's the change in y divided by the change in x. Okay, so we know what the change is here. It's delta x, so we'll leave that on the bottom. But the change in y is f at 1 plus delta x minus f at x. So what you can see is, if we just immediately make delta x equal 0, this expression, the slope that we need to form the equation for the tangent, because in this we're going to need both a slope and a point. Well, that point is easy because we're going to do this at 1, and the point would be then 1, 1. So we already know what the point should be. We just need to figure out what the slope is. Now, we have the slope, but we have that issue again, that we have delta x is going to equal 0 if we immediately kind of bring those 2 points together. So what we do is, the slope of the tangent, what we do is we will take the limit. So we'll let it get really, really, really close, infinitely close. So that we'll do delta x goes to 0 of the function f at 1 plus delta x minus f at x, all divided by delta x. Now what I can do here is I have the limit as x goes to 0, so that I have 1 plus delta x squared minus, I have 1 squared divided by delta x. Okay, so continuing on with that, I have the limit as delta x goes to 0. So what I need to do is I need to expand this. So I have 1 plus delta squared, so that's 1 plus delta x squared, and that's equal to 1 plus delta x, 1 plus delta x, and that's equal then to 1 times 1 is 1 plus delta x, and I have delta x times 1, so I have plus delta x plus delta x times delta x gives me delta x all squared, so that I have 1 plus 2 delta x plus delta x squared. Okay, so what I'm going to do is I'm going to substitute that in here. Oops. Okay, so I have 1 plus 2 delta x plus delta x squared minus 1, all divided by x, delta x. So I notice that I can cancel the 1 and the minus 1, so because that equals 0. So that I'm left with, push this up a bit. So I have the limit as delta x goes to 0. I have 2 delta x plus delta x squared divided by delta x. So I can also, I notice that I can factor out a delta x in this case. So I have the limit as delta x goes to 0. And I factor out the delta x, so I'm left with 2 plus delta x all divided by delta x, and I can cancel out those. So that I have the limit as delta x goes to 0, 2 plus delta x. And now I can actually let delta x go to 0 so that the limit of this is just equal to 2. Okay. So now to do the to do the equation of the tangent, I have a slope and I have a point. So the slope of the tangent, again, just to recap, is equal to 2. And we're doing this at the point 1, 1. So remember our equation for line, which is y equals mx plus b. So we just need to solve for b because we have the slope, which is 2, at the point x equals 1 and y equals 1. So I have b. So I have it equal to 2 plus b. So I bring the 2 over to this side. So 1 minus 2 equals b. b equals 1 minus, so that's just minus 1. Okay, so putting this all together, therefore, the tangent at y equals x squared for x equals 1 is y equals 2x minus 1. So let's see if I can draw this not too bad. So this is f at x is equal to x squared. So I have it at some point, let's say about here. And that's where it'll be 1. And there's the tangent. So it would roughly have a slope of 2. So this would be y equals 2x minus 1. And that's it. That's an example of finding a tangent to a curve at a point.